Welcome to our deep dive into modulation techniques. Modulation is a fundamental concept in communication systems, enabling the transmission of information over various distances and mediums. Whether it's your mobile phone, radio, or television, modulation plays a crucial role in ensuring your messages get delivered clearly and efficiently. In this video, we'll unravel what modulation is, why it's necessary, and how it forms the backbone of modern communication. Let's start by understanding the basic idea behind modulation and set the stage for exploring the different techniques used in the industry. Modulation refers to the process of varying a carrier signal in order to transmit information. Think of it as a way to encode your message onto a wave that can travel long distances without losing its integrity. This process is essential because raw signals, like voice or data, often can't travel far or may get distorted. By modulating these signals, we can send them over radio waves, cables, or optical fibers with much greater reliability. This foundational concept is at the heart of all wireless and wired communication systems. You might wonder, why do we need to modulate signals in the first place? The answer lies in overcoming the limitations of direct transmission. Unmodulated signals are susceptible to noise, interference, and attenuation, which can degrade the quality of communication. Modulation allows us to shift the frequency of the original signal, making it possible to transmit multiple signals simultaneously without interference. It also helps in efficiently utilizing the available bandwidth and improving the overall quality of transmission. There are several types of modulation techniques, each suited for specific applications and requirements. The main categories include analog modulation and digital modulation. Analog modulation techniques such as amplitude modulation (AM) and frequency modulation (FM) are commonly used in radio broadcasting. Digital modulation techniques like phase shift keying (PSK) and Quadrature amplitude modulation (QAM) are widely used in modern data communication systems. Understanding these types helps us appreciate the versatility of modulation in different scenarios. Amplitude modulation, or AM, is one of the earliest and simplest forms of modulation. In AM, the amplitude of the carrier wave is varied in proportion to the message signal. This technique is widely used in AM radio broadcasting, where audio signals are transmitted over long distances. While AM is easy to implement, it is more susceptible to noise and interference compared to other methods. Despite its limitations, AM laid the groundwork for more advanced modulation techniques. Frequency modulation, or FM, takes a different approach by varying the frequency of the carrier wave according to the message signal. FM is renowned for its superior sound quality and resistance to noise, making it the preferred choice for music and high-fidelity audio broadcasting. The technique is also used in television sound transmission and two-way radio systems. FM's robustness against interference has made it a staple in modern communication. Phase modulation, or PM, involves changing the phase of the carrier signal in line with the message signal. While similar to FM in some respects, PM has unique characteristics and is often used in digital communication systems. It forms the basis for more complex digital modulation schemes and is valued for its efficiency and reliability in data transmission. PM is less common in analog broadcasting, but plays a significant role in modern digital networks. Analog and digital modulation techniques serve different purposes. Analog modulation like AM and FM is best suited for continuous signals such as audio. Digital modulation, on the other hand, is designed for discrete data such as computer networks and mobile communications. Digital methods offer better noise immunity, higher data rates, and more efficient use of bandwidth. As technology advances, digital modulation is becoming increasingly prevalent in communication systems. Binary modulation is the foundation of digital communication. It involves representing data using two distinct states, typically 0 and 1. The simplest form, called binary amplitude shift keying (BASK), changes the amplitude of the carrier to represent binary data. This approach is straightforward but can be vulnerable to noise. Binary modulation is essential for transmitting digital information efficiently and reliably across various platforms. Amplitude shift keying, or ASK, is a digital modulation technique where the amplitude of the carrier signal is varied to represent binary data. A higher amplitude might represent a binary 1, while a lower amplitude represents a binary 0. ASK is easy to implement but can be affected by noise, making it less suitable for long-distance or high-speed communication. Despite its limitations, ASK is still used in certain applications like optical fiber communication. Frequency shift keying, or FSK, uses different frequencies to represent binary data. For example, one frequency might indicate a binary 1, while another frequency represents a binary 0. FSK is more robust against noise compared to ASK and is widely used in applications like modems, radio transmission, and RFID systems. Its reliability and simplicity make it a popular choice for many digital communication systems. Phase shift keying, or PSK, is a digital modulation technique that changes the phase of the carrier signal to represent data. The most basic form, binary phase shift keying (BPSK), uses two phases to represent binary 0 and 1. PSK is highly efficient and less susceptible to noise, making it ideal for high-speed data transmission. It's commonly used in wireless communication, satellite links, and Wi-Fi networks. Quadrature amplitude modulation, or QAM, combines both amplitude and phase variations to encode data. This technique allows for the transmission of multiple bits per symbol, increasing the data rate significantly. QAM is widely used in digital television, cable modems, and broadband internet. Its ability to carry large amounts of data efficiently makes it a cornerstone of modern high-speed communication systems. Pulse code modulation, or PCM, is a method used to digitally represent analog signals. In PCM, the amplitude of the analog signal is sampled at regular intervals and then quantized into a series of binary numbers. This technique is the standard for digital audio in computers, CDs, and telecommunication systems. PCM provides high fidelity and is resistant to noise, making it ideal for high-quality audio transmission. Pulse amplitude modulation, or PAM, is a technique where the amplitude of a series of pulses is varied according to the message signal. PAM is used as an intermediate step in converting analog signals to digital form and is also found in Ethernet communication. While simple, PAM is susceptible to noise, so it's often combined with other techniques for improved performance. Pulse width modulation, or PWM, involves varying the width of pulses to encode information. PWM is widely used in applications like motor control, power delivery, and audio synthesis. Its ability to efficiently control power and signal levels makes it a popular choice in both analog and digital systems. PWM is also used in LED dimming and other electronic control systems. Pulse position modulation, or PPM, encodes information by varying the position of each pulse relative to a reference. PPM is less susceptible to noise compared to PAM and PWM, making it suitable for optical communication and remote control systems. Its unique approach to encoding data provides advantages in specific environments where timing accuracy is critical. Wireless communication relies heavily on modulation techniques to transmit data over the air. From mobile phones to Wi-Fi and satellite links, modulation ensures that signals can travel long distances and penetrate obstacles. Advanced digital modulation methods like QAM and PSK are essential for achieving high data rates and reliable connections in today's wireless networks. Wired communication systems such as telephone lines and fiber optics also use modulation to transmit data efficiently. Techniques like PCM and QAM are commonly employed to maximize bandwidth and minimize errors. Modulation allows multiple signals to share the same physical medium, increasing the capacity and flexibility of wired networks. One of the key benefits of modulation is bandwidth efficiency. By carefully choosing modulation schemes, we can transmit more data within a limited frequency range. Techniques like QAM and PSK are designed to maximize the amount of information sent per unit of bandwidth, which is crucial for crowded communication channels and high-speed internet. Noise is an unavoidable part of any communication system. Modulation techniques are designed to minimize the impact of noise and interference. Digital modulation methods, in particular, offer superior noise immunity compared to analog methods. This ensures that your data arrives intact, even in challenging environments with lots of electronic interference. Multiplexing is the process of combining multiple signals for transmission over a single channel. Modulation makes multiplexing possible by allowing each signal to occupy a different frequency band or time slot. This is essential for maximizing the efficiency of communication networks, enabling services like cable TV, internet, and mobile networks to operate simultaneously. Demodulation is the reverse process of modulation. It involves extracting the original message signal from the modulated carrier at the receiver's end. Demodulation is just as important as modulation, ensuring that the transmitted information is accurately recovered and understood. Different demodulation techniques are used depending on the modulation scheme employed. Modulation Index is a key parameter that measures the extent of modulation applied to the carrier signal. In AM, it represents the ratio of the message amplitude to the carrier amplitude. The Modulation Index affects the bandwidth, power efficiency, and quality of the transmitted signal. Understanding and controlling the Modulation Index is crucial for optimizing communication performance. Carrier signal is a high-frequency wave that carries the information signal over long distances. Modulation involves altering the carrier's properties, amplitude, frequency, or phase to encode the message. The choice of carrier frequency and its characteristics directly impact the range, quality, and efficiency of communication. Spectrum allocation refers to the assignment of specific frequency bands for different communication services. Modulation techniques are designed to fit within these allocated bands, ensuring efficient use of the available spectrum. Proper spectrum management is vital for avoiding interference and supporting a wide range of services, from radio to mobile networks. Broadcasting services such as radio and television rely on modulation to deliver content to large audiences. AM and FM are the primary techniques used in radio, while digital modulation methods are increasingly common in television. Modulation ensures that signals can be transmitted over vast distances and received clearly by millions of users. Satellite communication depends on advanced modulation techniques to transmit data between ground stations and satellites. High-frequency carriers and robust digital modulation methods like QAM and PSK are used to overcome the challenges of long-distance transmission and atmospheric interference. Modulation enables reliable global communication via satellites. Optical communication such as fiber optics uses light waves as carriers. Modulation techniques like ASK, FSK, and QAM are adapted for optical signals to transmit data at extremely high speeds. These methods ensure minimal loss and high fidelity, making optical communication the backbone of modern internet infrastructure. Mobile networks from 2G to 5G and beyond rely on sophisticated modulation schemes to deliver voice, text, and data services. Techniques like QAM, OFDM, and PSK are used to maximize data rates and spectrum efficiency. Modulation enables seamless connectivity and supports the ever-growing demand for mobile data. OFDM is a digital modulation technique that divides the available bandwidth into multiple orthogonal subcarriers. Each subcarrier is modulated independently, allowing for high data rates and resistance to interference. OFDM is widely used in Wi-Fi, LTE, and digital TV broadcasting, making it a key technology in modern communication. Spread spectrum modulation spreads the signal over a wide frequency range, making it more resistant to interference and eavesdropping. Techniques like frequency hopping spread spectrum (FHSS) and direct sequence spread spectrum (DSSS) are used in military, GPS, and wireless communication for enhanced security and reliability. Adaptive modulation dynamically adjusts the modulation scheme based on channel conditions. When the signal is strong, higher-order modulation like 64 QAM is used for maximum data rates. In weaker conditions, simpler schemes like PSK are chosen for reliability. This flexibility ensures optimal performance in changing environments. Modulation techniques often work hand-in-hand with error detection and correction methods. These systems identify and fix errors that occur during transmission, ensuring data integrity. Techniques like forward error correction (FEC) are essential for reliable communication, especially in noisy or long-distance channels. Digital television relies on advanced modulation techniques like QAM and OFDM to deliver high-definition video and audio. These methods allow for efficient use of bandwidth and support multiple channels within the same frequency range. Modulation ensures that viewers receive clear, high-quality broadcasts. The Internet of Things connects billions of devices from sensors to smart appliances. Modulation techniques like FSK, PSK, and LoRa are tailored for low-power, long-range communication. These methods enable reliable data exchange between devices, supporting the growth of smart homes, cities, and industries. Software-defined radio is a flexible communication system where modulation and demodulation are performed by software rather than hardware. SDR allows for rapid adaptation to new standards and protocols, making it a powerful tool for research, development, and modern communication networks. As technology evolves, new modulation techniques are being developed to meet the demands of faster, more reliable communication. Research is focused on increasing data rates, improving noise immunity, and reducing power consumption. The future of modulation promises even more efficient and versatile communication systems. Despite its many advantages, modulation faces challenges such as spectrum scarcity, interference, and the need for backward compatibility with older systems. Engineers are constantly working to overcome these obstacles through innovative techniques and smarter spectrum management. Modulation is all around us, from the music we stream to the calls we make and the data we browse. Every time you use your phone, watch TV, or connect to Wi-Fi, modulation is at work behind the scenes, ensuring seamless and reliable communication. It's a hidden hero of our connected world. To sum up, modulation is a vital process that enables the transmission of information over various media. From analog to digital, simple to complex, each modulation technique serves a unique purpose in our communication networks. Understanding these methods helps us appreciate the technology that powers our connected lives. Let's quickly review some key terms: modulation, carrier signal, bandwidth, noise, multiplexing, demodulation, and spectrum allocation. Familiarity with these concepts will help you better understand the world of communication technology and its ongoing evolution. If you're interested in learning more about modulation techniques, there are plenty of resources available. Textbooks, online courses, and technical articles can provide deeper insights into the mathematics and engineering behind these methods. Exploring these resources will deepen your understanding and open up new opportunities in the field. Modulation techniques are used in a wide range of practical applications, from broadcasting and telecommunications to satellite and optical networks. Understanding how these methods are applied in real-world scenarios can help you appreciate their importance and inspire you to explore further. Thank you for joining us on this journey through modulation techniques. We've explored the basics, examined different methods, and seen how modulation shapes the world of communication. As technology continues to evolve, modulation will remain a cornerstone of our connected future. Stay curious and keep exploring the fascinating world of communication technology.